In this tutorial, I'm going to show you exactly how to size an electrical cable using the same step-by-step process used by professional electrical engineers. We'll start by understanding the design requirements, calculate the design current, select a suitable cable, apply correction factors, check the voltage drop, verify the cable against short circuit conditions, and finally, choose the correct protective device. By the end of this video, you'll understand not only how to perform the calculations, but why each step is essential for a safe and compliant electrical installation. Let's get started. Every engineering calculation begins with good design information. For this example, we'll be sizing a cable supplying a three-phase motor rated at 22 kilowatts. The motor operates from a 400-volt, 50 Hz supply, has a power factor of 0.9 and an efficiency of 95%. The cable length is 100 meters, and we've selected a 4-core N2XH copper XLPELSZH cable installed on a perforated cable tray. These design criteria form the foundation of every calculation that follows. Now we can calculate the design current. This is one of the most important values in the entire cable sizing process, because it determines the minimum current the cable must safely carry under normal operating conditions. Using the standard three-phase power equation, we substitute our motor power, supply voltage, power factor, and efficiency into the formula. After completing the calculation, we obtain a design current of 37.1 amps. This value becomes our starting point for selecting a suitable cable. With the design current known, we can begin selecting a suitable cable. Using the manufacturer's cable data for N2XH copper XLPE cables installed using reference method E, we compare the available cable sizes against our required current of 37.1 amps. The first cable capable of carrying this current is a 10 square millimeter cable with a current rating of 49 amps. At first glance, this appears to be a suitable choice. However, we're not finished yet. In the next section, we'll apply the correction factors to see whether this cable is still suitable under the actual installation conditions. Now that we've selected an initial cable, we need to check whether it can actually carry the required current under the conditions in which it will be installed. Manufacturers publish cable current ratings under standard reference conditions. However, real installations rarely match those ideal conditions. That's why we apply correction factors. These factors allow us to adjust the cable's current carrying capacity to reflect the actual installation environment. Let's begin with ambient temperature. Our installation has an ambient temperature of 40 degrees Celsius. As the surrounding temperature increases, the cable becomes less effective at dissipating heat. This means the conductor operates at a higher temperature, and the amount of current it can safely carry must be reduced. Looking at the correction factor table for 90-degree XLPE insulated cables, we find that an ambient temperature of 40 degrees gives us a correction factor of 0.91. This tells us that the cable can carry only 91% of its published current rating under these conditions. Next, we consider the installation method. Our cable is installed on a perforated cable tray using reference method E. A perforated tray allows air to circulate freely around the cable, helping heat escape efficiently. Because cooling is good, no reduction in current carrying capacity is required. Therefore, the installation correction factor is 1.00, meaning the published cable rating remains unchanged. The final correction factor is grouping. When several circuits are installed close together, they warm each other up. This additional heat reduces each cable's ability to carry current safely. In our example, 3 circuits are grouped together. Looking at the grouping factor table, this gives us a correction factor of 0.70. This is the largest reduction we've seen so far and has a significant effect on the cable's allowable current. Now we combine all of the correction factors. We multiply the ambient temperature factor of 0.91, the installation factor of 1.00, and the grouping factor of 0.70. This gives us a total correction factor of 0.64. We now apply this to the published current rating of our 10 square millimeter cable. The original current capacity was 49 amps. After applying the total correction factor, the adjusted current capacity becomes 31.4 amps. Our design current is 37.1 amps, so this cable is no longer suitable. This is an important lesson in cable sizing. Although the cable initially appeared to meet the design current, the correction factors revealed that it cannot safely carry the required load under the actual installation conditions. The next step is to increase the cable size and repeat the calculation. Using the same correction factor, we check the next available cable size. At this stage of the design, the 16 square millimeter cable gives an adjusted current capacity of 42.2 amps, which is greater than our design current of 37.1 amps. So, based on current carrying capacity alone, the larger cable appears suitable. However, we're still not finished. Current capacity is only one part of the design process. In the next section, we'll continue by checking the voltage drop to make sure the cable also meets the installation requirements over its full 100-meter length. Now that we've confirmed the cable can carry the required current, we need to perform another important verification. This time, we're checking the voltage drop. Every cable has some electrical resistance. As current flows through the cable, a small amount of voltage is lost along its length. If this voltage drop becomes too large, equipment may not receive its correct operating voltage, leading to poor performance, overheating, reduced efficiency, or even equipment failure. For this installation, we're supplying a 3-phase motor, so we'll use the standard 3-phase voltage drop equation. The calculation takes into account the design current, the cable length, the cable resistance, the cable reactance, and the power factor of the load. By substituting our project values into the equation, we calculate a voltage drop of 7.33 volts. To determine whether this is acceptable, we convert the voltage drop into a percentage of the 400-volt supply. The percentage voltage drop is calculated by dividing the voltage drop by the supply voltage and multiplying by 100. This gives a result of 1.83%. For a motor circuit, the recommended maximum voltage drop is 5%. Since our calculated voltage drop is only 1.83%, the cable comfortably meets the design requirement. So, the selected cable passes the voltage drop check. Let's take a moment to review what we've achieved in this stage. We calculated the voltage drop using the correct engineering formula and confirmed that the result is well below the maximum recommended limit. This means the cable will deliver sufficient voltage to the motor, allowing it to operate efficiently and reliably. At this point, we've successfully verified both the cable's current carrying capacity and its voltage drop performance. However, there is still one critical safety check remaining. Next, we'll verify that the cable can safely withstand the prospective short-circuit current before the protective device disconnects the supply. Now we need to carry out one of the most important checks in any cable calculation, the short-circuit check. Although our 16 square millimeter cable has already passed the current carrying capacity and voltage drop calculations, it must also be able to survive a short-circuit fault. During a fault, thousands of amps can flow for a very short period before the protective device disconnects the supply. To verify the cable can withstand this energy, we use the adiabatic equation. Using our fault current of 15,000 amps, a breaker operating time of 0.1 seconds, and the copper XLPE constant of 115, we calculate that the minimum conductor size required is 41.2 square millimeters. Our selected cable is only 16 square millimeters. That means the cable cannot safely withstand the fault energy. So although it passed the earlier checks, it fails the short-circuit calculation. This means we must revise the design. Our first attempt at increasing the cable size is 25 square millimeters. Using exactly the same fault current and operating time, we repeat the adiabatic calculation. This gives a thermal withstand current of 9,122 amps. Unfortunately, that's still well below the required 15,000 amps, so the 25 square millimeter cable also fails the short-circuit check. Whenever a cable fails this calculation, the solution is simple. Increase the cable size and calculate again until the cable can safely withstand the fault current. Safety always comes first. Before we continue increasing the cable size, it's important to understand where the 15,000 amp fault current actually comes from. This value is not guessed, and it doesn't come from the cable manufacturer. It comes from the electrical design documentation or fault level study for the installation. The fault level depends on the supply transformer, the electrical network impedance, and the location of the equipment within the system. For this example, the calculated prospective short-circuit current at the 11 kilovolt switchboard is 15,000 amps. This is the value we must use when checking that the cable can survive a fault until the breaker disconnects the supply. Always remember, the cable must be designed for the worst fault that could occur at its point of installation. Next, let's try a 35 square millimeter copper XLPE cable. Repeating the same calculation gives an adiabatic withstand current of 12,784 amps. Although this is an improvement, it is still less than the required 15,000 amps, so once again, the cable fails the short circuit check. This demonstrates an important engineering principle. Just because a larger cable carries more current doesn't automatically mean it can withstand the required fault energy. We still haven't reached a safe design, so we'll increase the cable size once more. Finally, let's try a 50 square millimeter copper XLPE cable. Repeating the adiabatic calculation gives a withstand current of 18,201 amps. This time, the cable's thermal withstand current is greater than the required fault current of 15,000 amps. That means the cable can safely survive the fault until the breaker operates. At last, we have found a cable that passes every design check. Although we originally selected a much smaller cable based on current carrying capacity, the short circuit calculation proved that it wasn't suitable for this installation. This is exactly why every cable calculation must include a short circuit verification. Now that we've selected a cable that satisfies all the electrical requirements, we're ready for the final stage, selecting the correct protective device. We've now confirmed that our 50 square millimeter copper X LPE cable satisfies both the current carrying capacity and the short circuit requirements. The final design step is selecting a suitable protective device. A circuit breaker has several important jobs. It must carry the normal operating current without nuisance tripping. It must protect the cable against overload, and it must safely interrupt the maximum prospective short circuit current. From our previous calculations, the design current is 37.1 amps, and the prospective short circuit current is 15,000 amps, or 15 kiloamps. When selecting a breaker, we need to satisfy two main requirements. First, the rated current, IN, must be greater than or equal to the design current. Second, the braking capacity, ICU, must be greater than or equal to the maximum prospective short circuit current. Let's compare a few possible breaker ratings. A 32 amp breaker is too small because it cannot carry the design current. A 40 amp breaker carries the current, but its 10 kiloamp braking capacity is lower than the required 15 kiloamps. Finally, a 63 amp breaker has a rated current above our design current and a 15 kiloamp braking capacity, exactly matching the fault level. This means the 63 amp 3-pole MCB satisfies all of our design requirements and is the correct choice for this installation. Congratulations! You've successfully completed the complete cable sizing process from start to finish. Together, we've defined the design criteria, calculated the design current, applied correction factors, selected the correct cable, verified the voltage drop, checked the cable against short circuit conditions, and finally, selected the correct protective device. This is the same logical process used by electrical engineers every day when designing safe and compliant electrical installations. Remember, good engineering isn't about guessing. It's about following a structured process, checking every calculation, and ensuring every part of the design complies with the relevant standards. If you follow this method, you'll consistently produce safer, more reliable electrical installations. Great work! You've completed the Cable Calculations series. If you found this tutorial useful, I'd really appreciate your support. Please give this video a like. Subscribe to Engineering Simplified for more practical engineering tutorials, and leave a comment below telling me what engineering topic you'd like me to cover next. Every like, every comment, and every subscription helps this channel reach more engineers, apprentices, and students around the world. Thank you for supporting Engineering Simplified.